Okay, welcome to lecture here. Get everybody in. All right, welcome to lecture. We're picking up chapter 6. We'll talk about chemical reactions. So again, we're kind of going backwards a little bit. We're going back to chapter 6, and then afterwards we will roll to chapter 7, I think, after that. And a couple of reminders. I did send out an announcement last week, kind of updating the schedule and what's going on this week and next week. So again, hopefully you saw that. We talked about it last time. But in case you didn't, again, make sure you take a look at the announcement. Again, it kind of explains what's going on every day. So you should definitely know what's going on and what we'll be discussing. And again, it should follow what we talked about last time in terms of the schedule. All right, so we're off to chapter 6 here. And chapter 6, we're going to talk about equations and balancing chemical equations. Again, how to go through the process of balancing chemical equations. And let's start it up here. All right. So first off, when we talk about sort of a chemical reaction, there's oftentimes visual sort of signs that a chemical reaction is taking place. Remember that a chemical reaction really is, right, a chemical change. And basically what that means is, as we talked about with chemical changes earlier on, what we start with and what we end with are two fundamentally different things. So it has sort of changed into new substances on the product side of the reaction. Again, as we talked about, there's no sort of physical way to get back our sort of starting materials. So it's changed fundamentally from where it started to basically where it ended. Not all sort of reactions, again, are sort of visual, like you'll get sort of a visual representation of, a reaction has taken place. Just for example, the formation of water, which, as we'll talk about, is one of the driving sort of forces for a chemical reaction to take place. And clearly, if you kind of are looking at a reaction that's taking place, you very often cannot kind of see the water being formed. It is obviously being formed. It is a reaction that's happening. But again, visually, you can't necessarily see it. Sometimes you can definitely see it, as we will see in this chapter, next chapter as well. Sometimes you could just mix two solutions together in some type of solid forms, which you obviously can visually see that happening and gives you a visual sort of indication of a reaction and it takes place. Here are some visual sort of clues that a reaction is take place. Again, some type of color change a lot of times will accompany a chemical reaction taking place. As I mentioned before, a solid being formed. Again, sometimes a solid is referred to as a precipitate and sometimes abbreviated as PPT, which again stands for a precipitate that has occurred. Bubbles is also a very good sort of example of something occurring in terms of a reaction. And usually bubbles indicate some type of gas has basically been formed. So that's usually those bubbles that you see in a chemical reaction is the generation of, again, some type of gas. Heat and or flame, obviously flame is visual, heat as well. So for example, if you were holding a test tube and the test tube got hotter, that would mean that the reaction, for example, is exothermic. So it's given off energy and your hand gets hotter because it's holding it. Or vice versa, if you're holding a test tube and perhaps it gets colder, your hand may feel colder, and that may be an example of an endothermic reaction taking place. Again, you might not visually see anything happening, but kind of the feeling of the heat, your hand getting hotter or colder, again, indicating that some type of reaction is basically taking place. So here again are some of those examples. Here we have a lot of bubbles being formed here. Again, those bubbles pretty much indicative of some type of gas that has been generated. Obviously a flame here, like when we light a Bunsen burner, some methane, a little bit of oxygen from the atmosphere there gets this reaction going. And also here again, you can see some bubbles probably forming here. Maybe if you look, you'll also maybe see some change in color of the metal. The metal may also sort of, I don't want to say disappear, but dissolve as it's going through this chemical reaction. So again, these are all sort of examples of reactions taking place. So what is a clue that a chemical reaction is taking place? Again, here in this particular case, we see obviously the bubbles that are forming. Again, an indication that some type of gas has been generated or is being generated. And obviously in this particular example here, it would be bubbles. That's kind of the electrolysis of water. What we're seeing here, we're actually taking liquid water here and breaking it apart into hydrogen gas and some oxygen gas. And again, that is the bubbles that we are seeing happening here in this particular reaction. Again, we're kind of breaking the reaction into its elements there in that particular case. Also here, if we look at this here, this is a sort of a titration, which is a common sort of chemical experiment there. And the reaction that's occurring, for example, is our color change that we're seeing here. Again, starting kind of pinkish in color. As you can see, after we added a whole bunch of solution to it, it turned blue. Usually that's some type of indicator that's in that solution to indicate that basically a reaction is taking place. And so here a color change would be the example that we would be looking at in this particular reaction. Obviously, in this particular reaction here, we're taking two liquids. You can see the first liquid is colorless. Second liquid, kind of a yellowish color. But when it forms here, this is a precipitate here. Again, PPT, sometimes the abbreviation for that. And this is this yellow solid that's being formed. And as we'll talk about in, again, probably more so the next chapter as well, when we do make a precipitate, sometimes people think it needs to be like a rock hard precipitate, you know, like a baseball sort of, you know, as hard as that may be. And it doesn't. Again, it could just be some cloudiness that are forming, some particles that are being forming. If you kind of took that and centrifuged it down, you would get a pretty good compact solid that's formed that again wasn't there as well. And you know, for a chemical reaction to occur, or just really for a reaction to occur, there's really sort of three driving forces for a chemical reaction to occur. So three of the driving forces are some of the ones that we have seen here. It is a precipitate that's being formed. The formation of water is another sort of driving force for a chemical reaction to take place. And lastly here, as we will talk about a little bit more in the next chapter as well, an electron transfer. So when we think about reactions occurring, or chemical reactions occurring, those are really the three sort of really important things that, again, are sometimes referred to as the driving forces for chemical reactions, basically to take place. So how do we represent chemical sort of reactions taking place? We use chemical equations basically to represent what is going on in a chemical reaction. And here's an example of a chemical equation. And this is basically the reaction of methane with oxygen. This is, again, what sort of happens when you light a Bunsen burner. And there's really two sides to a reaction or an equation. First side is the reactants, and those are pretty much your starting materials. So those are your starting materials in a chemical reaction. And then on the right-hand side of the arrow, those are our products there. And those are obviously what has been formed as a result of your chemical reaction taking place. So sometimes, though, in terms of the arrow, we do see a number of things sometimes written on top of the arrow. Sometimes you may see a little triangle, and that usually means heat. You may also see things like PT or H plus and other sort of metals and stuff written up or on top of the arrow. Those usually are what are referred to as catalysts. And as we'll talk about, a catalyst is something that typically will speed up a chemical reaction, but is not considered a reactant. It's not considered a product. It is there really just to make that chemical reaction occur faster. So again, it's really not a reactant and not a product here. Again, just there to speed up the chemical reaction. Sometimes as well, you even see water sort of written on top of the arrow. And when you see water written on top of the arrow, usually that means that we're dissolving something in water. Although in a vast majority of the cases, when we look at the chemical equation, it does represent usually a chemical reaction that's taking place. And again, in a chemical reaction, as we can see here, basically only the elements basically rearrange. So we don't lose any elements along the way. We don't gain any elements along the way. We have the same amount of carbons on the left as we do on the right, and hydrogens on the left as we do on the right. Obviously not in this case, because what we're looking at right now is what is referred to as an unbalanced equation. We don't have the same numbers of each of the elements on each side. But as I was mentioning here just a second ago, sometimes we do actually use chemical reactions to represent maybe physical changes. So for example, we can sometimes write a reaction that looks something like this. This is really a physical change that's happening. We're taking water from the liquid state to water in the gas state. So I would say most of the time we use chemical equations to represent chemical reactions and chemical changes. But you can sometimes use a chemical equation to represent more of a physical sort of change that's happening. And that would be the case there with the water example. In that case, we started with water, we ended with water. They're both obviously the exact same thing fundamentally. So what we're seeing there is a physical change. But most of the time, our equations do represent those chemical changes that are occurring. Any questions on that there? So because in most of the time when we talk about sort of a chemical change occurring or a chemical reaction occurring, really, there's really two processes that are happening. One is essentially everybody on the reactant side, which is our starting materials, they essentially are just going to break all their bonds. So they're essentially just going to break apart completely. And basically, they're going to reassemble on the other side, which is the product side. And again, like I said, if you started with like 4 carbons on the left, you should end with 4 carbons on the right. Those carbons may just be in a different sort of substance on the product side than they are in the reactant side. But we should have sort of that conservation of elements. And as we'll talk about here in just a second, that's sort of the whole purpose of balancing, is that sort of we don't lose anything along the way. So again, we should end and start with the same number of elements, again, just in different sort of arrangements. A couple other things that we obviously commonly also see in equations are the states of everybody. And we sometimes see S written, in parentheses, L written, G written, or AQ written next to the formulas. And these usually will represent the states of those guys in the equation. So obviously S is solid, L is liquid, G is gas state, and AQ is our aqueous state. And aqueous basically means a water environment. And very often people sometimes are confused again about sort of the difference between, excuse me, these two sort of states, liquid and aqueous. And there actually is a difference between liquid and aqueous. If something is a liquid, it's a pure liquid by itself. So for example, if we had just plain old H2O, that is a pure liquid and would get the L symbol next to it. But if we took something like water, which is a pure liquid, and put it together with something like sodium chloride, which is a solid, and we mix these guys together, the solid would dissolve into the water, basically, those ions, and we would get what we would refer to as sodium chloride with the aqueous symbol next to it. Aqueous usually means a solution, and a solution basically is a homogeneous mixture. So that is sort of the main difference between those two states. Again, L is really just some type of substance like water that's all by itself, nothing else in it, just pure water. While aqueous usually means that you take something and a lot of times dissolve it in something like water, and you make basically this solution that's homogeneous. You don't usually see the solid or anything like that. Obviously, it just looks like a liquid, for lack of a better sort of example there. So that is the difference between those two things. Again, one referring to something by itself, which is our L in the liquid state. The other one also sort of in the liquid state, but it's basically two things together, something like sodium chloride and water, which makes a sodium chloride solution. Any questions on that there? Okay. So let's talk about balancing these equations and what we want to do. So sometimes you do have to start with, or you do start with what is sometimes referred to as the unbalanced equation. And the unbalanced equation is like what we were looking at earlier there. We have our CH4, which is our methane, plus our O2, CO2, and water. So this is our unbalanced equation. And really, when we go to balance an equation, there's a lot of sort of ideas on what to do. The easiest thing to sort of balance. And when we do balance equations, the most important thing, or it's really a couple of most important things. First off, you do need to use all whole numbers when you balance, or when you have a balanced equation. And also really important in that sense is when we go to balance, and the only numbers we change are the coefficients. So it is only the coefficients, those numbers in front are the only ones that you should change. You should never change anything that is like a subscript or anything like that in the formula, because if you change the subscript, then you change what it is. So what I mean by that is, obviously, if you have water in an equation, you should only put a number here in front. You should never change this and go, oh, I'll just make it like H3O because that will help better. A, this probably doesn't exist. And B, if you change that bottom number, you're changing really what it is. So you should never, ever change any of those subscripts or anything like that. Only those numbers that come in front as you go to balance equation. Other crazy things sometimes people do is you should never like put a big number in between or anything like that. So again, no big numbers or anything like that in between elements in a formula. We want to keep the formula kind of the same, obviously, and we just want to change our coefficients. So when you go to balanced equation, you definitely want to make sure when you have a properly balanced equation, all of those coefficients should be whole numbers. The other thing is they should be the simplest set of whole numbers. And what I mean by that is sometimes people can balance equations differently. Sometimes people could see larger numbers to help get it balanced. And you could balance equations sort of with different numbers in front. So for example, if I had 4a plus 2b goes to 6c. And we'll just pretend that this ends up being a balanced equation. You got the same number of everybody on each side. But when we look at these coefficients, they are all whole numbers, but we essentially can reduce everybody down by by 2 basically. So if this was the case and you balance it using these numbers like 4, 2, and 6, this technically would not be the properly balanced equation because you can reduce all those guys down. And the properly balanced equation in that example would be something like 2a plus b gives you 3c. Again, all whole numbers, the simplest set of whole numbers for each of those guys. And those are really the two sort of things that you want to definitely make sure when you balance the equation that A, you do have the same number of elements on each side, but you also have the simplest set of whole numbers for your balancing thing. So in our example here, one way sometimes people approach sort of doing these things is you can kind of make a table of what you got going on. So in our unbalanced equation, which is up here on top, we can a lot of times, and it's very helpful just to make like a table of what's there. Like we have carbon, hydrogen, oxygen. And on the left-hand side, for example, we have one carbon. Right-hand side, we also have one carbon. Left-hand side, in terms of hydrogen there, we got 4. And obviously on the right-hand side, we have 2 hydrogens. Left-hand side there, we have 1, 2 oxygens. Left, I get my left and right, sorry. Right-hand side there, we have 3 oxygens. I'll get my right and left correct here in just a sec. So, when you're approaching something like this and you're looking to perhaps balance everybody out, what you want to do is maybe make a table, because it kind of gives you a good idea what's going on. You can call this side perhaps the reactant side. This side here can be the product side. And it gives you maybe a direction as to where you want to go to try to balance these things. And for example, if we look over here, carbon is balanced on each side. Hydrogen is not, and oxygen is not, but hydrogen probably be the easiest thing to balance. So we could put a 2 in front of that water like we have there. Let's grab a different color here. So we could throw a 2 in front of it. When we throw that 2 in front of it, on the right-hand side, we still have 1 carbon. Hydrogen, 2 times 2 is 4. And our oxygen now is 2 in this guy, and 2 times 2 is 4 in that guy. That then gives us pretty good direction that to balance it, we just need to now come to the other side and again change the coefficient to a 2. That gives us 1 carbon, 4 hydrogens, and 4 oxygens. So as we can see down here, by changing again just the coefficients, we're able to get a balanced equation, and we have exactly the same number of each of those elements on each side, which is ultimately the goal here. We have 1 carbon on each side. We have 4 hydrogens on each side, as our table shows. And we also obviously have 4 oxygens on each side, which also we see on our table. Any questions on that there? So I sort of jumped the gun on that there, but again, those are very common things that are oftentimes shown in a chemical equation. Now, when we approach a chemical equation, and especially if you're sort of approaching a chemical equation sort of in 2 ways that it commonly happens. One way, as we'll see here in the next sort of example, is perhaps we have everything written in words. So very often people, when they don't have the equation given to them, but they have things either in words, or maybe they have the reactant side, but not the product side, people oftentimes make mistakes because they try to balance the equation and write the chemical formulas at the same time. You always want to follow this sort of path here. Always want the correct formulas first, and then balance. So, and it's very common in a case where we have, our reactants given to us, and you need to kind of figure out what's going on over here on the product side. And it's super common. People try to do both of those things together. They try to like balance and write the formulas. And what usually happens in those cases is you will end up with the completely wrong formula for a substance. And in addition to having the wrong formula, you'll be there all day trying to balance an equation that will not balance because you have the wrong formula. So always important, correct formulas, just like we did with nomenclature and writing chemical formulas, and then go back and change the coefficients and balance. So it's super important to kind of do it in that order. And again, I can't tell you how many people do it in the wrong order or do both of those steps together. So when we look at this sort of equation, blue light shines on a mixture of hydrogen and chlorine gas to form hydrochloric acid. So to write the unbalanced equations, other things that people often miss as well is when we talk about hydrogen gas, you got to remember that those are diatomic molecules, right? So people oftentimes will just write H here because it's hydrogen. They think it's just one guy by itself. But remember, hydrogen gas, oxygen gas, nitrogen, chlorine, fluorine, bromine, those are all diatomic molecules. So you want to make sure you get them right. Reacts with chlorine gas, which is also that group 7, which also comes as a 2 to form hydrochloric acid, which is our HCl. So, we should have something like this in terms of the unbalanced equation, which looks like it is D in this case here. And again, at this point, it's not balanced. We would want to go back and balance it using coefficients. And in this case, you could just make a little table on the reactant side, product side, for example. You have 2 hydrogen on the left-hand side, 1 on the right, 2 chlorines on the left, 1 on the right. So if we wanted to get this to the balanced equation, we would need a 2 in front of the HCl, giving us 2 and 2, and we would have a balanced equation in that case. question on that there? So same idea here. If we look at this one here, we want to write the unbalanced equation for the reaction of elemental carbon and elemental hydrogen to produce methane gas. So we're looking at elemental carbon and hydrogen to produce methane gas. When we see words like elemental, sometimes people will use something like molecular as well. That's basically these elements in their natural form. So something like carbon in its natural form is just C, no charge, nothing like that. Elemental hydrogen is hydrogen gas, which is H2. And again, to produce methane, which is CH4, one of those sort of a common name guys that we talked about when we talked about type 3 guys. And it looks like perhaps this is C would be the right answer here. Again, here, this is not balanced, right? To balance this, we would need, again, if you did sort of a table, reactant side, product side here, we have one carbon, 2 hydrogen on the left, and 4 on the right. So to balance out, we simply just need to put a 2 in front of that. And that would give me 1 carbon and 4 hydrogens. We would now have a balanced chemical equation at this particular point. Any questions on that so far? So a couple of these things that I think we sort of talked about here. The idea here is we want to continue to change the coefficients on the reactants and products with the understanding that we don't lose any elements as this process is occurring. So thus, as I mentioned a number of times already, you know, if you start with 7 carbons, you should end with 7 carbons. Again, they may be in different formulas on the product side, but you should have sort of that conservation of the elements. And we achieve that by putting coefficients in front of these formulas to balance them. Now, it does has to be, as I mentioned, those two things, all whole numbers. And again, if you could reduce down everybody by a common number to get to a whole number, then you should do that. Otherwise, technically, you don't have a balanced equation at that particular point. So let's take a look here. Let's go through the process here. We sort of maybe did, or we'll go through this guy together here. If we wanted to balance this equation, we have hydrogen gas and oxygen gas combined to form liquid water. Again, if it was not given to you, you want to make sure first off that you are starting with the correct formulas. So this again right here would represent our unbalanced equation with our states that are there. Again, making a table like we've seen there will help us sort of get an idea as to what's going on. 2 hydrogens on the left, 2 on the right. We got 2 oxygens on the left, but only 1 on the right. So again, the table sort of directs you where a good place to start would be. In this particular case, we need to fix the oxygen. So to fix the oxygen, again, we want to put a number only in front. When we do that, that now gives us 4 hydrogens and 2 oxygens. And very common in balancing, we can fix one thing and then kind of screw up the others. So at this point, the table helps us sort of visualize where we need to go next. Since we now have fixed the oxygen, we need to fix the hydrogen. And again, we could do that by simply putting a 2 in front of it, giving us 4 hydrogens and 2 oxygens. And this would be the balanced equation with the proper coefficients. Any questions on that there? Okay, so let's roll through this. And what's on the screen is what we just did in 2 seconds rather than 42 slides here. But I'll scroll through it so you can see it in case you want to look at it later. But it's essentially what we did. Again, you kind of want to move from one place to the next. Make sure you put those coefficients in there. And you should, if you have an understanding of what those states are, kind of put, the states in your equation as well. Again, in the next chapter, we'll talk about some ways that you'll know if something, for example, is a solid, if it's aqueous. We'll have some more ideas about how to figure that out in the next chapter. But usually a lot of times you should include them if you kind of know them, and obviously, especially if they tell you to do so. All right, here. All right, why don't you give this a go and see what you come up with here? Why don't you balance this equation, take a minute or two, and then we'll talk about it. Okay, so let's take a look at this one here. So again, I highly recommend kind of doing a table. It's very helpful sometimes, make one of reactants, make one for your products and your elements there, which is iron. Probably write it better than that. I'll try it again. All right, here, go with iron. We have oxygen. So left-hand side, we have one iron. Right-hand side, we have two irons. Left-hand side, we have three oxygens, one there and two there, gives us three. On the right-hand side, we also have three oxygens. So it seems not too bad. It seems like we're pretty much balanced except for the iron. So that's probably a good place to start. So perhaps you laid a two up there. And when you do that, that gives me two iron. On our left-hand side here, we have two oxygens in our front one, still two in the back, gives you four. So at this point, you may be going, well, I want to kind of balance these guys here, but the oxygen on the right here is by itself, but it's with iron. So if I do anything to try to balance the oxygen on the right, then I got to mess up the iron on the left there and start changing coefficients. So sometimes when you look at a balancing equation, sometimes you need to kind of think a little creatively So clearly I just put a number here, which means I really don't want to kind of go back and start erasing numbers. So if I think about trying to keep this guy exactly the same where he's at, because that keeps the iron balanced, I really have 2 oxygens available to me now. And on the other hand side, I have 3 oxygens. So really, when I think about this oxygen here, I actually just need like 1 more oxygen, right, to get me to 3 on both sides. So I can't do 1 here, right, because I have a 2 on the bottom. So a way that you could kind of do that is I basically need to turn this 2 into a 1. And to do that, you basically can do something like a fraction, for example, 1 over 2. If I do 1 over 2 times 2, that equals 1, which means now if I looked at my equation here, I still have 2 iron. I also now have 2 oxygens in the first guy. 1/2 times 2 in the second guy gives me 1 more for a grand total of 3. So at this point, technically speaking, this equation is balanced. I have the exact same number of elements on each side. Now, you may be saying to yourself, didn't you say that when it's all said and done, you do need to have all whole numbers? And the answer is yes, you do need to have all whole numbers. So what that means is we can use a fraction here to balance it, but we do need to get rid of the fraction before it is completely balanced correctly. So what we want to do is then multiply everybody by a denominator, basically. And when we do that, what we will end up with is 4 of the FeOs plus 1/2 times 2 is 1 oxygen, gives me 2 Fe2O3. And if I did everything correctly, my equation should still be balanced. So let's take a look real quick. We have 4 irons on the left and 4 on the right. We have 4 oxygens here plus 2 more give me 6. We also have 3 times 2, which is 6 oxygens. So this would be the correctly balanced equation. And this is a nice example that it shows that although you cannot have a fraction or a decimal in your correctly balanced equation, you can use a fraction to help you balance the equation, but you do have to get rid of that fraction when it's all said and done by multiplying by the denominator. Now, usually this occurs kind of like this situation where you have an element in a couple of things with its natural form, sort of elemental form, and one on the other side is usually where it occurs. Now, you may ask yourself, how did I know kind of 1/2 was the right sort of number that I needed? So there's a very simple sort of rule to follow. Basically, the top number is the number you need. So if you remember, we were talking about we need to basically turn this guy into a 1. And on the bottom, it should match whatever's to the right of it. So the bottom number here should match these two guys. Question on how to balance an equation. They're using a fraction. Okay, so the key is you can definitely use fractions to balance equations, but it is not properly balanced until you get rid of the fraction. So you got to clear it by, again, multiplying by that denominator. Any questions on that one there? And again, sometimes you may not need to use a fraction. Like I said before, some people can see maybe larger numbers that will work that you can maybe reduce down or something like that, and it's perfectly fine. But again, fractions are sometimes helpful. Any questions on that there? All right. So I'm why don't you try the next one? Your question, explain the fraction part of it. So if your question was, why do we choose that fraction? Sort of before we started there, we had 2FeO plus O2 went to our Fe2O3. Again, in terms of the iron, at this point when we were there, we had 2 on each side, so it was balanced. It was all good to go. In terms of the oxygen, like I said, we had a total of 3 on the left and 3 on, not 3 on the right, 4 on the left. There you go. 4 on the left, and 3 on the right. So the reason I didn't want to kind of do anything with this guy here is because at this point when we were here, we have already fixed the iron. So if I start changing the coefficient here, it's going to mess up the iron that's over here. So with that in mind, what I know is because I sort of locked that 2 into place, I had 2 oxygens for sure, which meant at this point I only had 2 oxygens on this side, 3 on this side, which meant the only place I could put a coefficient for oxygen would be here. And I needed to make it like only 1 oxygen. And that's how I got to my fraction. 1 was the number I needed up on top to match the number down here. And by doing a half of O2, that gives me basically 1 oxygen. And that would balance it. So again, the idea there is you could use a fraction to sort of help you balance it. Other questions on that? All right, so why don't you try that one? Why don't you try that one, see what you come up with, and we'll talk about it. Okay, so let's take a look here again. Good place to start is a table. So reactant side, product side, we have looks like some calcium, oxygen, and carbon going on here. On the left-hand side, we have 1 calcium. Right-hand side looks like 1 calcium. Left-hand side, we have 1 oxygen and 2 oxygen on the right. And left-hand side, we have 1 carbon. And then we have 2 carbons there and 1 more there. It gives me 3 carbons. So calcium looks balanced. Carbon, not so much. Oxygen, not so much. So again, sometimes the best approach is sort of the simplest thing to fix. So since carbon's in a couple of things, as we can see here on the right-hand side, maybe we should leave that for the last. And the oxygen here is probably the easiest to fix right off the bat. So since we only have 1 oxygen on the left-hand side, we could just put a 2 in front of it. When we do that, that then gives us 2 calciums, gives us 2 oxygens, and 1 carbon. So in this particular case, again, here we fixed the oxygen and kind of screwed up everything else that's going on there. So the next easiest thing to probably balance should be our calcium. Again, carbon with multiple things. So we're going to save that maybe to the end. So putting a 2 in front of our calcium on the right-hand side gives us 2 calcium, still 2 oxygen. And now in terms of our carbon, we have 4 here and 1 more here, which gets us to 5. And this is again why we left the carbon here for the end. since carbon was in multiple places on the right-hand side, now we could very easily fix the carbon by putting a 5 in that place. Gives us 2 calciums, 2 oxygens, and 5 carbons in that particular case. And we would have a balanced equation. Any questions on that there? Okay. So as we've been talking about, again, the number of atoms on each side of the elements, of each element on each side of the equation, again, should be the same. We do not touch any of the subscripts or anything like that, only the coefficients. And again, we do need that simplest whole number ratio of what is present. And as we saw in that example, again, you can do a fraction if you need to, if that's helpful. All right. So again here, why don't you give this one a go here? We want the balanced equation for the reaction of carbon with hydrogen and to produce methane. So see what you come up with for the balanced equation. Okay, so on this one here, again, very common people mess up on this part of it here. So remember, pretty much most of the things on the periodic table comes as ones when they are in their sort of natural form. So carbon would just be C. Elemental hydrogen, molecular hydrogen, hydrogen gas, again, a reminder, not H, but H2, which is a diatomic gas, and CH4, again, being our methane, which is also a gas. So if we take our sort of balancing approach here, we have carbon, we have hydrogen. Left-hand side, we have 1. Right-hand side, we have 1. 2 hydrogen on the left and 4 on the right. So not too bad here. Put a 2 there on the left-hand side. Going to get us a balanced equation. And that looks like perhaps B would be a winner, I think, in terms of the answer. Question on that particular one there. So again, very important, especially if you have in words or you're predicting the product side, make sure that you get the right formulas down. Okay. Now, sometimes when we balance equations, sometimes you'll end up with some polyatomic ions that are in the equation and also found on both sides of the equation. And they're found in their sort of exact same state, if you will. So what I mean by that, if you look at something like NO3 here, our calcium nitrate, we have NO3. We also have NO3 over here. If you look on the left-hand side, we have phosphate here, PO4, and we also have phosphate over there. So sometimes it's easier to keep those polyatomic ions together while you're balancing them rather than going element by element. You definitely can do element by element, but because they are polyatomic ions, you have a lot of like, I need to multiply in and all that kind of stuff. So, you do have to kind of be very careful as you go element by element. Sometimes it's much easier just to basically keep those polyatomic ions together as long as they look exactly the same on both sides and balance them almost as sort of whole units. So what I mean by that, for example, is if we look at the phosphate, we have one phosphate on the left, so one PO4 on the left and two on the right. So we can easily sort of fix that by putting a 2 in front of here. What that does is it gives me two phosphates on the left, but it immediately also changes my sodium to 6, which tells me where I should go next, which would be over here. And I would need to put a 6 in front here. That's going to give me 6 sodiums, but now also give me 6 of the nitrates. And I can fix that by putting a 3 over here, giving me 6 nitrates and now 3 calciums, which is actually what I need. So sometimes it's easier and a lot faster when you're balancing equations that have polyatomic ions on both sides to keep those polyatomic ions together and balance them as like whole units rather than having to go every element and sort of factoring in the twos and all that kind of stuff. Sometimes people will make mistakes on that. Any questions on that there? All right, so why don't you try a couple here and see what you come up with. All right, so why don't you balance these two and then we'll talk about it. Okay, so let's take a look. So it's our top one here. We do have some polyatomic ions. It does look the same on both sides. They look, we only got one there. So again, we could kind of do a table. And if we keep that sulfate sort of together here, we have one on each side. We also have, in terms of barium, we have one on each side. So that's looking good. And in terms of chlorine, we got one on the right and two on the left. And lastly, our sodium here, two on the left and one on the right. So at this point, we could try to fix the sodium or the chlorine. Should be easy. We're going to put a 2 in front of it on the right. And when we do that, we still have the 1 SO4, the 1 barium. Our chlorine now becomes 2, and our sodium becomes 2. And we are actually balanced in that particular case. Any questions on that particular one? Now, when you come down here to the bottom one, there's a lot of letters going on. Again, you could do it element by element. You got to distribute in like the 4s and all that kind of stuff, and the 2 on the right-hand side. But again, we see acetate here, and I see acetate over here, which is a polyatomic ion. I also see chromate on each side. And in this particular case, we could go any approach if you want. You could start with the acetate. So I got 4 on the left. I only have 1 acetate on the right. So I could fix that by putting a 4 in front. When I do that, that does give me 4 of the acetates. It then gives me also 4 of the potassium, which is where I should go next. So on the left-hand side, I have 2 potassium. So to fix that, I'll put a 2 in front of the potassium. That fixes the potassium. That also now gives me 2 of the chromate, which is good because that's what I'm looking for. So that's all good. And we still have our 1 lead on each side. So at this point, if we sort of count up everything, and I think that's everybody. Yep. We have, again, 1 lead on each side. We have 4 of the acetates on each side. And we have 4 of the potassiums on each side. So we are balanced. So very often with those polyatomic ions, if you kind of keep them together, things sort of fall into place at some point, and that's usually a good thing. Any questions on that there? All right. I think we might have done this one, earlier. So we'll skip ahead. I think we did this one earlier. Let's do, why don't you do this one here? Balance this one up. Okay, so let's take a look here. And to answer your question, in terms of usually balancing equations, you don't necessarily have to show work. So just a properly balanced would be probably sufficient. For your own purposes, though, I definitely would make some tables so that you can make sure that they are balanced. I can't tell you how many tests I've seen over the years where people think they're balanced and they're really not. So usually the table is very helpful for yourself as well. So just in case you thought it was balanced, it hopefully should help you decide it's not or it is and stuff like that. But usually not too much work for balancing other than obviously putting the proper coefficients in. All right, so here again, we can kind of take the approach and what we got going on our reactant and product side. So starting here, we do have two carbons on the left, one on the right. Hydrogens on the left is 6. On the right, it is 2. Oxygens on the left there is 2. And again, in terms of oxygens, we got it in a couple of places here on the right-hand side, and that's going to give us 3. So not too much balanced here. So probably, again, the easier approach here would be to fix the carbon. We can fix the carbon pretty easily by putting a 2 in front of it. On the right-hand side, that gives me 2 carbons, still 2 hydrogens. Now, in terms of oxygen, I do have 4 here, and one more makes 5. So we fix the carbon. Again, probably the next easiest thing to fix would be the hydrogen. So since we have 6 on the left, we can put a 3 in front of the hydrogen on the right. Going to give us 2 carbons. 3 times 2 is 6 hydrogens. And now our oxygen is up to 4 here and 3 here, which is 7. Any questions so far? Okay, so at this point, clearly we got pretty much everything balanced by putting these coefficients on the right-hand side, and we need to balance the oxygen. We clearly don't want to start changing the numbers on the right-hand side. Otherwise, we're going to change the numbers of everybody. So really on the left-hand side, we have 2 oxygens. On the right-hand side, we have 7. So we really need to turn that 2 into a 7. So again, this is a place where we can do a fraction. Again, the top number is the number we need, which is 7. The bottom number will match this number, which is 2. That means that we would now have 2 carbons on the left, 6 hydrogens, and when we take 7 over 2 times 2, leaves us with 7 in terms of the oxygen. At this point, again, technically it's balanced, but it is not correctly balanced because we have a fraction. So remember, as we talked about earlier, you can use the fraction to balance, but then you need to get rid of it. So we're going to multiply not just the fraction by the denominator, but everybody that is there. And if we do that, that gives us 2C2H6 plus 7O2 gets us 4CO2 and 6H2O. And again, if we didn't screw up anything here, we should still be balanced. So we got 4 carbons on the left, 4 on the right, 12 hydrogens on the left, and 12 on the right, and 14 oxygens on the left. On the right-hand side, 8 oxygens there, and 6 more give me 14. So this would be our properly balanced equation. Any questions on that? Balancing equations, fractions, polyatomic ions, any of those things? Okay, that should wrap up chapter 6 here then in terms of balancing. I think. All right. We've got a couple more examples actually. So here, why don't you do these last 2 and then we'll wrap it up, I guess. Okay, let's take a look at this since we're getting to the end here. So, taking sort of the same approach, not that approach. Okay, so if we make a table here, basically got carbon, hydrogen, and oxygen for our first one, and I think our second one as well. Left-hand side, we have 4 carbons. Right-hand side, 1. Left-hand side, 8 hydrogens, and 2 on the right, and oxygens on the left, 2 and 3 again, 2 there and 1 there. Not much going on here in terms of balancing, so easiest fix would probably be the carbon. We will lay up a 4 there. That's going to give us 4 carbons in terms of hydrogen, still 2. And oxygen now becomes 8, and 1 more gives us 9. Again, here, probably the simplest thing to balance would be our hydrogens at this point. We could put a 4 in front of there. That is going to give us 4 carbons. We are going to have 8 hydrogens. And now in terms of our oxygen, that is 4 times 2, which is 8, plus 4 more. That's a lot of math there. I'm going to go with 12. So that's good. Now that we saved our oxygen for the end here, working out pretty good. I think a 6 there will do that. Going to give us 5, 8, and 12. So we should be balanced at that point. Question on that particular one there. Again, only changing the numbers in front, only the coefficients here. So let's take a look at our bottom one here, same sort of table. We have our reactants, we have our products, carbon, hydrogen, oxygen. On the left-hand side, we have, looks like 6, I think. Right-hand side, we have 1. 14 hydrogens on the left, 2 on the right. And oxygens, 2 on the left. And again, our kind of same situation here. 3 on the right-hand side. Probably same approach here. Usually pretty good approach on these type of reactions, which are combustion reactions. Start with the carbon. So carbon is going to be 6 here. Going to get us 6 carbons, still 2 hydrogens. Oxygen is 12 in the first one, and 1 more gives me 11. Again, same idea here. The next easiest thing to fix is our hydrogen. 14 on the left, 2 on the right. So a 7 would probably be a winner here. 7 as our coefficient gives us 6 carbons, 14 hydrogens, which balances that. And now our oxygen is 12 in the first one on the right, and 7 more. 12 and 7 is 19. So we now have everything balanced except for our oxygens. And again, we're in that situation like we saw earlier. Oxygen by itself in its natural form, oxygen and a couple of things over here. So again, we're going to shoot with a fraction to help us. 19, which is the number we're looking for, goes up on top. On the bottom should have a matching number to this guy, which would be 2. That gives me 6 carbons, 14 hydrogens, and 19 oxygens. Again, at this point, it is balanced, but we do have to clear it because it is not properly balanced and not correctly balanced. So again, here we're going to multiply by the denominator, giving us 2C6H14 plus 19O2, 12 CO2, and 14 waters. Again, multiplying that 2 all the way across. Gives us 12 carbons on each side, 28 hydrogens on each side, and 19 times 2, 38 oxygens on each side, 24 in the first guy, and 14 oxygens in the second one, and we would be balanced at that point. Any questions on that particular one? All right, questions on balancing or anything in this chapter? Okay, so now this does finally finish chapter 6. All right, so we will stop there, obviously, for lecturing right now. As we mentioned last time, we're going to continue lecturing there in lab, so we're going to go on to chapter 7. And I will see everybody in about 15 minutes. So make sure you put here if you haven't done so, and we'll continue on.